All right. Good afternoon, everyone. Welcome to ARENA's webinar on Hot Decarbonisation Opportunities. I'm sure we'll have a couple more folks join over the next few minutes, but in the interest of time, I'm going to get going so that we best leverage the time that we have. So very quickly, before we get stuck in, this webinar will be recorded and later posted as part of ARENA's knowledge sharing. So just so that you're aware that that's the case. And then before I get into a couple of logistics for today, I'd like to do just an acknowledgement of country, where ARENA acknowledges the traditional custodians of country across Australia and their continuing connection to land, sea, and community. And we also pay our respects to elders past and present. So what have we got on the table today? So first of all, my name is Tanya Hodgson. I'm an investment manager in ARENA's business development and transactions team. And I do a lot of work in the industrial space where we're looking at accelerating decarbonisation solutions. So on the cards today, we'll first hear from Jared Leake, who's the CEO of A2EP. I'm sure many of you are familiar with the good work that A2EP does in this space. And you'll have the opportunity to ask Jared some questions before we switch over to hear from 3 case studies, who I'll introduce as we go, from industrial entities including G&K O'Connor, Real Pet Foods, and Bindaree Food Group, before we do some very quick wrap up at the end. So some practical guidance for today. You'll see that there is Q&A functionality on the webinar, so please ask questions. You also have the opportunity to upvote questions that you want to see answer. So we'll do our best to answer any quick questions.
Okay, I've lost Tanya. Anyone else?
Hi,
Yeah, I think we lost her.
Yeah, he's gone. Yeah.
Jared. This is Atik. I'm from Real Pet Food. We have our engineering department head trying to join into the meeting. I don't know whether you can help out with that.
I can help with that, Atik. I'll send a link in the chat for anyone to pass forward to others if that's a suitable solution. Well, hopefully we have the rest of the ARENA team as well who might be able to help. But let me get on that link for you while Tanya reconnects.
Sure.
I'm sure Tanya's thinking, yeah, my internet was fine all day until now.
And then 100 people join a call.
Yeah, exactly.
That's strange. Tom, maybe you want to take the lead there? I don't know.
We've just heard from Tanya. Apparently, we've had a blue screen of death incident. So we'll pass on to Jared and get started with that one.
Fantastic. All right, thanks, Anthony. We'll skip through to the next slide there, and just a very quick introduction on A2EP. On the next slide, you'll see this is our actually a month or two old, so we've got some members to add to that one. But industry association, focus on energy productivity and decarbonisation, a very broad spectrum of members, which one of our great strengths is. So we really reach right across research, OEMs, utilities, energy consultants, and a lot of end users as well. So that's where we fit in, and been doing a lot of work in renewable heating over the last many years. I'll give you an example of that coming up in the moment of where we've come from. This slide here shows where this issue of emissions on heating fits in. The black line showing renewable electricity and trending down fast, which is great as we get more solar, wind, and batteries and what have you into our energy mix. But if you look at this sort of, I'll call that maybe a turquoise, greeny blue line there, it is due to be the #1 source of emissions under this stationary energy part, going above the sort of a mauvey dotted line there for transport. So it is due around 2030 to be the #1 source of emissions in Australia. And yes, while it shows a downward trend, there is a lot of work to be done there. If you look at the next slide and sort of see where we've come from and where we are in Australia, we are probably a bit behind what Europe has implemented a lot more technologies and options, certainly when it comes to biomass. But we're probably ahead of the US, who had a decade or so of stagnation there. But a lot of the work was done in terms of publications around 2017 to 2019, mapping out the opportunities and the technologies. And there's just a few of those publications shown on the top there. And then they've been built on over time. With ARENA, we did a series of 30 or so studies come 2020 and 2019, where we looked at all the different options for technologies, and that's where we had a lot of our foundational knowledge on what works and where and how. And really, we've been working hard to build on that over the last 4 years since then. Other work has been done by the Race for 2030 CRC, and if you were to look up their opportunity assessment for decarbonising heat, there's some great information on there. Finally, there's the harnessing heat pumps for net zero by the Energy Efficiency Council and A2EP, published a year and a half ago or so. Along the bottom, just a few sample projects. The very first heat pump, industrial heat pump on ammonia, went into Thomas Foods installation in South Australia in 2012, a Mayakawa compressor project there. And so we've had them around for quite some time. MSM milling, that was an ARENA funded biomass boiler. I think that went in about 2019, 2020, so been operating for quite some time. A 4 megawatt boiler project there. Another ARENA funded project was this Hardwick's heat pump project, about a megawatt of heat capacity there. I've got some more info coming on that one. And another one of note is the Graphite Energy project, the electrical thermal energy storage project done at Mars Wodonga by Graphite Energy. A fair few more in there, and I'll go through in a few more details in just a moment. Latest work done by A2EP is a boiler mapping exercise. We think we've reached somewhere around 20 to 30% of the major boilers and burners across Australia to find out what their intentions are in terms of decarbonising their heating and a little bit of a time frame for that. The data that we had did cover a fair bit of industry. Although there was some gaps, we didn't do too much in wood processing and bricks, cement, steel, or oil and gas, but we did cover off pretty well through alumina and food and beverage and chemicals and mineral processing. So we think we got a fairly good snapshot. And on the next slide, you'll see one of the key findings was that nearly 40% of the burners and boilers out there are due for replacement in the next 5 years, which is the good news. Certainly, if you've just bought a boiler or a burner in the last few years, that's going to make the financial case extremely hard to wear new technology as well as the depreciation on the old technology. So plenty of opportunity certainly here and now. On the next slide, you'll see that a bit of a vector of where things are headed. Electrification was by far the number one, followed by biomass and then biogas. A very large chunk is still undecided, and that was through the many interviews we did over the last 12 months or so. So there's still a fair bit of work to do, certainly with studies and what have you. So electrification, biomass, and biogas, that's the three main areas that we think the opportunity is. With that, we sort of, what's an energy presentation without a little bit of Sankey? And so this is how we sort of see that evolving then, if we put a few more numbers on that. And you'll see most of that natural gas and black coal is what's doing that, the heavy lifting at the moment. A bit of a breakdown on that coming up in the next slide. But we see that moving towards bioenergy and additional renewable electricity. A lot of opportunities start becoming evident with energy efficiency once you start looking at things like electrode boilers or hydrogen as well. So we certainly can't leave that out. We also get a lot of efficiency gains as we use things like heat pumps or mechanical vapor recompression, which delivers, say, 3 or 5 or even 10 times the amount of thermal energy for one input of electrical energy. The next slide just shows a little bit about where we're at in a bit more context there. So if we say that industry using 44% of Australia's final energy demand, of that about 52% is used for heating. Of that, around 70% is or more is from fossil fuels. So This is a really large chunk of the story for decarbonising industry and Australians' emissions as well. A very big piece of work, good piece of work done by ITP there. If I just go back one slide there, Anthony, is just show that little bit of a breakdown there where we sort of see things headed. And for those higher temperature requirements for bricks, cement, glass, we expect a lot of that to be done by biogas and biomethane, some hydrogen, and some of this electrothermal energy storage. This mid section around when you need to deliver around 200 to 300 degrees, you've got a lot of choice between biomass and boilers and what have you. And the bottom section, the lower temperatures, we certainly see heat pumps and MVR, solar thermal and geothermal to absolutely dominate there. Let's call that 150, 200 degrees and below. That's going to be the most economical solution there, likely going forward. A little bit on the specific technologies on the next slide, you'll see a little bit of a breakdown on that CapEx and things. So geothermal, very cheap, almost no OpEx, just some pumping once you get this running, but the cost of the drilling is quite expensive. Great opportunities in Australia. With the War Memorial in Canberra has just opened up with a fabulous geothermal heat pump solution, but also if you look at the Latrobe Valley, we've got an enormous resource there for just straight geothermal, and it has been used for aquatic centre heating and what have you, and the same in WA around Perth. Biomass, we've got a fabulous resource. This is where we're definitely behind most of Europe. They've really gone to good lengths to get the most out of their biomass resources. And I mean waste biomass, waste wood and sawmill offcuts and residues. It is a more expensive technology, but you can certainly with a low feed or fuel cost, it is very economical. Biogas and biomethane, excellent for these high temperatures, but the cost to develop a new project that will give you the gas that you need is quite expensive, and there is definitely regulation problems holding that back at the moment. Solar thermal really can be quite economical at definitely below 100 degrees, even say up to 200. And so we see that playing a reasonable amount of decarbonisation, even though it's a bit quiet, or rather quiet over the last 10 years. We think that's going to more to happen there. We're watching that one. For electrification options on the next slide, you'll see that we've got the likes of hydrogen, essentially unlimited as long as you've got the water and you can get the renewable electricity there. But the high cost per gigajoule, we expect that to maintain for many, many years, probably looking at that 2030, 2040 type solution for the technology. Heat pumps and MVRs, that's absolutely here and now. The products are here, the solutions are ready, and we're now getting a lot of the installation examples out there to learn from as well. Heat pumps are really pushing into that 160 degree range, and more happening in the steam-based heat pump. And then mechanical vapor recompression is pushing towards 240 degrees as well. So that's moving along pretty well. ETES, electric thermal energy storage, great for those higher temperatures and for those mid-ranges as well. You've got the likes of graphite I showed before, MGA thermal and Rondo on the big end, and I've got a slide for that. Finally, the other one is electrode boilers, the other main electrification option. And we've already had these in Australia, like at Tasmanian dairies, and we're seeing some more installations likely to happen in the next 12 months as well. Definitely higher in the capex compared to a standard natural gas boiler, but certainly a great decarbonisation option, and gives you that drop-in fuel situation where you provide steam at the same temperatures and pressures that you've had before. On the next slide, I'll just jump over this one really quickly, and I think most people will get the pack. I've just tried to show where these different solutions and options sort of fit in with a little bit more granularity of different types of heat pumps and the like. So if we get into a few examples now, you'll see this next one coming up is a mechanical vapor recompression project that went ahead in New Zealand a year and a half ago, which is using for a sugar refinery and can perfectly be replicated across our refineries in Australia, 5 or 6 refineries that we have, but also in many other applications wherever you're doing evaporation. So that could be fruit juice, Sugar mills could employ this to free up more of their bagasse. But anywhere you're doing evaporation around Australia, this is going to be an excellent viable solution. I draw your attention to that 18 times more efficient than a single step. So like a COP of 18, it's really one of the most unbeatable technologies to decarbonise that we have available. On the next slide, you'll see that it is being considered on a very large scale, and Alcoa has been looking at this for running their digestion and spent liquor evaporation plants. And so they see it as a very good opportunity. They've been doing some trials over the last year or two, again, with ARENA's assistance. And so we think that's going to lead to some more projects down the line as well. So that's definitely an indication from the likes of Alcoa. This is going to be a big part of the decarbonisation story. On the next slide, if we move a little bit to heat pumps and something a bit more specific now, another ARENA helped along project, this one at Kyneton there for Hardwick Meats, now owned by the Kilcoy Global Group. They've got hot water needs for their abattoir, and the heat pump producing 75-degree hot water for them. At the moment, still being stepped up with a gas boiler to up to 82 degrees. But I understand they're doing a lot of tweaks and what have you, and there's further growth in the performance of that heat pump done by Hokda and with Mayakawa compressor, where they're pushing up to about 80 degrees already. So not much gas used there at all. This is a fabulous system, fully integrated with solar and wind and batteries, and with the existing waste heat from the refrigeration plant. A fabulous project there and very good results. Very happy with that one. They are. On the next slide, to show you a bigger example. So it's not just about 1 megawatt. It could be up to 130 megawatts. This is MAN's Energy Solutions heat pump to produce steam. And right now, Fonterra in New Zealand is going through a study to see how they can utilize such technology. So you can take the heat pump all the way from your house for a kilowatt or two all the way up to 130 megawatts. So it's quite the technology, and with the high COPs, I'm sure we'll see more of that. On the next slide, we've got introducing Mars here, and here's Paul Matushka, who's one of our absolute leaders around the country for pushing these solutions. And on the next slide, you'll see that the graphite energy installation there at Mars Wodonga, providing steam straight into the existing network there, and had a really good seamless integration, and that's delivering steam at a very similar cost to what they were having for their boiler. So it's proving very economical and a good solution. Again, this can be done on a large scale as well. So this is a plant in Germany, a chemical plant, and they're looking to implement the Rondo technology. And you see the bottom left corner, that's these bricks that they have to store the heat in, heated up with electrical resistance, and then that draw on that heat to produce hot air and create steam as they needed. And so this is it on the multi-megawatt hour type of scale, and we expect to see more of that. Electrode boilers now, just the one case there for you. We had this at our recent Renewable Heat Conference. Paddy McMillan from MVM in New Zealand. This was an exciting project, up to 14 megawatts from a steam electrode boiler. They're getting fabulous results and loving this. And the interesting point about this one, most people found, was that it required 17 different partners to bring all that together. So it's quite complex, and to make a successful project, it needs a lot of partnerships. To finish off with a couple of biomass examples, this is one from Enriva for Van Wyck Flowers there in Lyndhurst, and it's in Victoria. And on the next slide, you'll see this is a 3 megawatt boiler, biomass boiler, and that's providing heat for the glass house in the evening, and I understand also CO2 during the day for fertigation to help with the glass house growth rates as well. That requires a big thermal storage, so I think they've got some 2 megalitres of hot water tank, an enormous hot water tank, but that's what you need to build that hot water up during the day and use that heat overnight. Finally, a second last case study here is a very large, that can be done on a very large scale as well. And so here's 80 megawatts of biomass boilers being done by Borg in Mount Gambier for their processes there on particle board. The very final one is a biogas case, and this is from JBS, the biggest food company in the world, are moving on with capturing their waste and using a covered anaerobic lagoon to get the biogas from that and use that in their boilers to displace natural gas. Getting great results for that, great returns, and we're sure we'll see many more of those projects happen in the meat processing industry. And I can take a breath now. And sorry about the overload, but that gives you hopefully a good flavour for what's happening and where we're at with things there. Is Tanya make it back online? That's the question for the day.
What a perfect time to blue screen. It's Murphy's Law. Thank you so much, Jared. That was excellent timing to the minute. All online, we have an opportunity before we move on to ask Jared any questions that you might have. I can't see any coming up in the Q&A, but now's the time if you want to add those, and if they're specifically for Jared, just pop the name there. We can always also come back if you want to mull over your question, and we'll have an opportunity at the end as well. But while I give a bit of a pitch of ARENA's work in this space, please have a think about any questions that you have for Jared, and we can make sure that we address those. So let me talk a little bit more to ARENA's work in this space. And Anthony, if you don't mind just going to the next page. Last year, ARENA announced $2.3 million worth of funding for 11 industrial-focused feasibility studies. And each of these feasibility studies were in the range of $100,000 to $500,000 grants, and they supported $4.5 million of total project cost. So this specific portfolio was particularly targeting engineering studies, but it's worth noting that ARENA actually supports along the project maturity spectrum. So we can support engineering studies, whether that's pre-feasibility, fees, or detailed design, but we can also support trial, pilot, demonstration, and deployment as you get up that maturity curve to ensure that the technology or the solution that you have in case is adequately proven. So the work in this space looked at 6 different industrial sectors. It covered alcoholic beverages through warehousing, aquaculture, waste, meat processing, and food manufacturing, and looked at a range of different decarbonisation solutions. So we had everything from electrification options to using geothermal heat, to electrifying heat and using heat recovery, plus anaerobic digestion and energy efficiency options. So ARENA today has funding for work across the, let's call it, industrial decarbonisation space. More than happy to provide relevant links programs, but just so that you are aware, there's $440 million worth of funding focusing on low emissions industrial decarbonisation solutions. That covers regional industrial facilities under the Powering the Region's industrial transformation stream, but also covers metro opportunities under the smaller national industrial transformation stream. So maybe Jared, just before we move on, and this was the end of my pitch for ARENA's portfolio, but there was a question just asking why Funbake Flowers went for a biomass boiler rather than heat pumps. So perhaps we address it here before we all forget the context.
Yeah, absolutely. I don't know the specific reasons, but I do know generally why that would happen. And that's often about the electrical constraints. So that project was a 3 megawatt boiler, and so you would need at least a 1 MVA connection, and that's probably a little bit hard if you're out in the regions, and that would be a much larger than what a typical horticultural grower would have already, so may have required that upgrade there. Heat pumps are also more expensive per kilowatt or megawatt of energy supplied. And the other one would be that biomass may well have the edge because of the CO2 that you can get from that, and fertigation and the improved growth rates that you'll get when you have that higher CO2 concentration inside the glasshouse. Certainly, we've seen several glasshouse and nurseries go ahead with heat pumps, say when they do have that connection available, and they may want maybe don't need the CO2. So we've definitely seen projects go ahead. I think it was Zaldesh Farms in WA, just one example, went ahead in the last 6 months, 12 months ago, with their heat pump installation there, and that seems to be, from what I understand, performing very well. So yeah, it's worth considering, I'd say, for horticulture, worth considering both options and seeing what suits the best.
Perfect. And then one more question for you, Jared. For companies that are likely candidates for both heat pumps and MVRs, do you think that grid constraints, so for example, like distribution network capacity, is that going to make it harder to justify the investment behind these types of solutions?
Absolutely. So what we'll see is if it's just a local transformer upgrade, just in hardware for a heat pump project, probably MVR as well, that'll probably double the size of your project there. But it can get worse. If you would need to force a local substation increase, that's more likely about 5 or 6 times that cost again. And so this can be a major hurdle. And this is where this ETES does come in handy, where you can have that bit more flexibility, and you may not trigger these sorts of upgrades, or even thermal storage. So you've really got to consider, carefully model how much thermal storage. We suggest at least around 20% is required for thermal storage. One, to take those peaks off so that you don't require such a large connection, and also just so that you have the equipment running more often and you get more value out of that. And of course, energy efficiency first, always. Demand reduction, that's absolutely where you start. So if your average demand is 1 megawatt or so, and you can get that down 800 kilowatts, then you're really going to make that much more economical. So energy efficiency, the first fuel, always done first.
Got it. And then one last question. Do you have any recommendations for good resources on ramping up on heat pumps particularly, but also the rest of the technology options that you mentioned?
In terms of, there's a website that we run called futureheat.info that has a lot of case studies on there across the different technologies already, and that usually helps people get a feel for them and understand where they are. But in terms of understanding how best to implement them, how best to design and size and thermal storage, yeah, that really is going to energy consultants that have experience in this space, that will come on site and really understand your heating demand profile and do the work there. But it is an emerging space. There's not an enormous list of energy consultants that have that experience and capability in this area, and so there's still some learnings, and we're still going to get better at this and how to optimize this. But there's a lot of factors to consider. This is not just a pure chemical engineering, process engineering problem. This is looking at your electrical supply constraints and the electrical design and what have you. So it's quite complex, but we're getting experienced people out there that are doing more and more studies, getting better and better at this too.
Perfect. Thank you so much. Okay, I'll take that opportunity to introduce our first case study. And if we maybe just flip forward, we're going to hear first from Megan Williams, who's the Sustainability and Innovation Manager at G&K O'Connor. And G&K O'Connor looked at red meat processing energy and emissions, and they received a $440,000 grant from ARENA for an $880,000 study. So I'll pass over to you. Megan, you're on mute.
Sorry, start again. Hello, everyone. I'm here today with Hugh and Seymour, our energy consultant from Northmore Gordon, who have been our principal consultant working with us on this project. The aim of this project has been to close the loop on our processing energy and emissions. I'm going to move through the first we'll move through the first 8 or so slides quite quickly, just because of our time constraints today. The purpose of this project was to assess, first of all, the first milestone was to implement a metering and monitoring system on site. And then the second milestone was to use the data from that metering and monitoring system and basically carry out a bit of a 360-degree analysis of options we had available to decarbonise the site. So I might hand over to Ewan. Do you want to say anything more about the project purpose, Ewan?
I'll just quickly cover off that we received funding from ARENA and AMPC, the Australian Meat Processing Corporation, to undertake the study, and it was around focusing on viable roadmaps to decarbonise its red meat processing plant. Can I do this? Yes. Okay, and if we just step through, there wasn't a specific legal requirement to decarbonise. We were trying to assess this for the entire red meat industry, and the only target we have from industry is around AMPC's recommendation to align with Paris commitments. That's all for this. Step forward.
Yeah, I guess just to say a little bit more about that, the Paris commitments are to decarbonise best case scenario by 2040, but the Paris commitment is really to decarbonise by 2050. But the pressure to decarbonise is actually coming from our supply chain and trading partners. So, and also the uncertain future we have around principally the cost of gas. Obviously, the electrical network is decarbonising, but the cost of gas is highly uncertain. For example, between 21-22 financial year and 22-23, our gas price increased significantly, nearly doubled.
Certainly. All right, we'll step on to milestone 1. So milestone 1 was to implement a metering and monitoring system. This was needed because there was no existing baseline or measurement to create one. So we had to go about measuring the existing plant operations, and that's specifically plant activities on site, scope 1 of burning natural gas, and emissions from the grid. We didn't cover scope 3 emissions as part of this study. What the metering and monitoring system encompassed, beforehand, it was literally people with clipboards. There was a manual system. They would, on an ad hoc basis, collect data, and it wasn't centralised anywhere. Afterwards, we implemented a system in which we monitored electricity and gas across the abattoir, render, wastewater and refrigeration plants, hot and cold water in both the abattoir and render plants, gas on each boiler. There are 3 of them on site. Steam, we monitored the entire steam boiler. It's in the render plant, and products in and out of the abattoir and render plant and wastewater flows. The monitoring system itself that we've created here has automated and centralized data collecting in a historian. It displays trends and reports data using an automated dashboard. The dashboard provides energy trends and breakdowns, KPIs or energy performance indicators for the whole site and each of the abattoir, render and wastewater plant, a build your own chart function with all of the data points available, and an ability to download data for further analysis. This has helped us create a thermal breakdown for the site, a Sankey diagram you see here. It shows heat from supply through to discharge, and the purpose of doing this is identifying heat loss for reuse and opportunities. Significant things you can see on this chart. You can see the ammonia compressors have a large opportunity for heat recovery as it's currently being rejected out of the cooling towers. and the wastewater system has a great deal of heat being sent down to wastewater, and as well as you can see losses in the boilers and the waste heat evaporator on site. Stepping forward, this is looking at milestone number 2. This is the integrated scenarios portion. In order to provide the necessary detailed understanding we needed, we had 4 technical reports completed as part of this study. It was John's Environmental did one on covered anaerobic lagoon and biogas. Northmore Gordon, my company, completed one on thermal process integration and electrification. We had Beam complete one on solar PV, batteries, cogen, and an economic feasibility, and we had NHAR produce a grid and peak demand study. Technologies we assessed as part of the roadmap were solar, so that is on-site PV, and thermal storage that input electricity and output steam that Jared spoke about earlier. Biogas, we covered anaerobic lagoon to produce biogas in use in the steam boiler. Energy efficiency projects such as waste heat recovery, heat pumps producing hot water and combined with thermal energy storage. Electrification, so that is directly converting natural gas uses across to electricity, such as electric boilers. Biomass boilers, in the other category there, that's using logging waste. We ruled out electric batteries due to payback and the sizing for the required storage we needed, and we didn't proceed with cogeneration due to concerns about reliability and energy cost exposure concerns. For integrated scenarios we considered with this study, we had basically a technology focus for each one. Solar LED maximises the amount of solar capacity installed and utilising the excess solar for thermal storage. Biogas LED, which is using a covered anaerobic lagoon with the on-site waste processing to substitute a portion of the natural gas, and that's used for steam generation in the render plant. Efficiency LED, so those are the cost-effective energy efficient technologies, and we put the biomass boiler into that scenario. And the final one is full electrification, which was replacement of all natural gas consuming equipment with electric alternatives, on-site storage and procurement of renewable energy or on-site generation. Our evaluation methodology, we used a multi-criteria decision matrix, and that is scoring each project in each scenario against the criteria important to G&K O'Connor to produce a combined scenario score. We then applied a valuees assessment across the scenarios. This enabled us.
I think it's just worth mentioning there that one of the really effective things we did in this process is we basically had a project group made up of experts. So Northmore Gordon are at the table, John's Environmental Group, Beam, myself as representing GKO and NHAR. And it was really, it was very good to have all that expertise at the one table applying the methodology. I think it worked really well and we got an intelligent result from doing that.
Yeah, I think it helped produce a balanced result. So each of us have our own preferences, and it helped. I think we were able to check each other and come up with a solution or a possibility with G&K's priority or focus in mind.
Yeah, challenging each other.
That happened quite a bit.
Yeah. So I'll just move on to the next slide, the summary of our analysis. So do you want to, yep.
I can take this one if you'd like, Megan. I'll hand it to you for the next one.
Yeah.
The outcomes we've shown here is monetary and emission savings. We don't have a particular regulation requiring change, so the pathway was driven by business drivers. And we're looking here for the scenario that delivers the best value for money. These charts here show, is your priority cost saving or is it carbon saving? Because the two don't necessarily align between the different scenarios. Just pointing, the other category here includes biomass boiler in the energy efficiency led scenario and thermal energy storage with spot price exposure in the full electrification scenario. Move on to the next one, Megan, which you can cover, please.
Yep, so this is a summary of our analysis. What came out of our analysis is there was no single clear technical or financial solution to transform to low or no carbon emissions. And we really, the outcome of the study really demonstrated that the efficiency-led approach is really the first line to go, first path to travel down, consistent with Jared's findings. It's got the best payback. It's got the best, the most efficient capital outlay, and it's most positive in terms of net present value. Just move on to the next slide. So we've laid out. So I guess the approach we're taking is to enshrine energy management into our organisation as business as usual. And this Bill Gates quote is quite a good one. Most people overestimate what they can do in 1 year and underestimate what they can do in 5 to 10 years. And I think it's definitely an incremental path. We've got positive feedback from our senior leadership team in relation to implementing the efficiency-led scenario. I think the fact that it's proven technology, they have confidence in it. It's the most appealing payback and highest net present value. The first thing that we really need to do is introduce an energy management system, which we see as the catalyst to cultural change on site. And then the other thing, which we really, and this draws on Jared's discussion actually, Jared mentioned in his presentation that 40% of boilers that they've discovered are getting towards the end of their life. Well, our 65% of our gas use on site is from our render plant boiler. And our render plant boiler, which is a 6 megawatt boiler, is coming to the end of its life. So one of the immediate actions that we would like to bring forward is really doing a deep dive into how we avoid replacing it with like for like going and buying a brand new boiler. So we've already got a grant from Sustainability Victoria to look at mechanical vapour recompression in the render plant. We'd also like, when you talk, Jared, about electrical constraints on site, that is definitely a consideration for us at the moment, and we're still a low voltage customer, but it really raises the issue of whether we should be converting to become a HV customer. We have a good relationship with AusNet, and I think with the deep dive that we need to do, AusNet need to be at the table as part of doing that deep dive. Ewan and I have talked about it in detail, and Phil Woodward, who's been involved in our study significantly as well. And really, the best result's going to be from having a multidisciplinary team and really working through all the issues. Do you want to say anything here, Ewan, in terms of the energy management system? And
yeah, so the only thing is we usually approach energy management systems from an opportunity cost point of view of how much can we save in terms of operational cost. It's with G&K as a client, it's actually quite a useful management tool in order to change the focus of the operations group. So we're going to be using it there, as Megan said, for cultural change, and we don't expect that to be a quick process. We hope to be able to achieve improvement and demonstrate improvement over time, but we expect it to take quite a while.
Yeah. This is nearly our last slide, where we've actually done an indicative roadmap timeline, starting to map out how we'll roll out our energy efficiency projects. And you'll see in our energy efficiency timeline, we've got gaps where we're providing sufficient time to calculate our VEGS credits, which are an important financial credit for the cash flow. But you can see here with the projects that over a 10-year period, as we move through the projects, and obviously I think, this is an iterative, indicative roadmap because the technology is constantly changing, and what might be the right thing to do today, in 12 months' time, there may be a better solution. So, but what it shows is that it's achievable within 10 years to fully decarbonise. And a massive kick that free kick that we get is this emissions factor. The fact that the electricity grid is greening in any regard. So we reduce our carbon emissions by that. Really the main issue is our gas consumption. We need to get off gas. So would you like to say anything else, Ewan? Or
we've shown this here. The improving emissions factor contributes, the dark blue at the top of this graph. The improvements in Scope 1 emissions is in orange here. So that is the significant work that G&K O'Connor have to do themselves.
Yeah.
Maybe just last minute.
Okay, so the last minute, let's move on to the main lessons that we've learned from this project. We've learned that metering and monitoring is the first step to quantify carbon emissions and develop a decarbonisation plan. We've been through real complexities in retrofitting a metering system into existing operations. It's been tough. It's taken a lot of collaboration between players. We realised that training and cultural change is absolutely critical to change and decarbonising. There's no single clear technical or financial solution, no silver bullet that will transform our operations. We see it as an iterative journey. That makes most sense for medium-sized businesses, starting with minimising our demand through energy efficiency, energy productivity, as Jared calls it, and production improvement measures and adoption of proven technologies. And thank you for being here today and listening to our presentation.
Thank you so much, both. I think really informative and helpful to see what this looks like in practice and how you start that journey. So definitely a wealth of expertise. We're going to move on now to our second case study, and we'll hear from Raj, who's the Sustainability Projects Director of HPE, who helped support the work at Real Pet Foods. They received a $250,000 ARENA grant for a $500,000 study. Handing over to you, Raj.
Thank you. Real Pet Foods is a rather largish gas consumer with about 220 terajoules a year of gas consumption, quite an energy intensive in terms of producing pet food. This study covered two sites, one in Sydney in Ingleburn and the other in Yatala in Queensland, but they do have other sites as well. So the main objectives here was really focused on Scope 1 emissions, analyzing heat and mass transfer to achieve a first principles approach, identifying opportunities. So we wanted to target about 40% reduction, reuse and recycling of energy. That was quite an optimistic sort of number that we were aiming for. Mainly focused on Scope 1, as I said, and then looking at setting the scene for our Scope 2 emission reduction in terms of offsetting and alternate fuels. So detailed design of all the projects that we'd undertaken. So we were spade ready to go forward, having capital estimates, cost benefit analysis and investment proposals ready to go, and also then quantifying the remaining footprint. So it's not that dissimilar to a lot of other studies, except that our focus, coming from a process engineering point of view, was very much a first principles calculation approach alongside metering. So the approach we took is essentially do a process mapping, calculation of heat demand, and quantify the energy footprint from first principles, and then compare them against metering that we had installed. So it was a bit of an accident, unintended, where metering took a little bit of time to actually come online, because as part of the project we were doing both the study and installing the metering. Which actually did force us to do a lot more detailed investigation and observing to get our energy and mass balance accurately. And then when we compare it against metering, we were able to go how much was the exact losses, and are these losses what you'd expect naturally from conduction, convection, and acceptable losses versus losses that are. Step back a slide, please. In terms of seem to have stepped a slide forward by mistake. So essentially identifying opportunities where we could reuse heat within the same process. So what temperatures were needed, how much was wasted. So I call that reuse or reduce, because in the same process it's in balance. The second opportunity we'd look for then is to reuse it in another process where there is the need to actually make sure the two processes are aligned in terms of demand and supply. And the third is to then look at what low grade heat in terms of low temperature heat is generated that could be recycled with the use of some energy to boost that back up. Then, of course, the next steps were to do the detailed engineering design, CapEx review, and quantify our overall footprint. So just a summary of where we got to. So we did build a very detailed heat and mass balance from first thermodynamic principles. We found many initiatives that we'd originally thought would be feasible when we went into this process didn't quite work as we expected. Energy metering is vital, as the previous speakers did say, but there was a little bit of an unexpected benefit in the metering coming a little bit later. But yes, metering being installed first is absolutely important. We found ways of measuring instantaneous mass flow of product versus energy. So that was harder than expected. Not often all processes have all of their parameters monitored or controlled. So getting down to that nitty-gritty of per kilo of product, how much heat was being used from a first principles point of view was a little bit more challenging than we expected. We should have and we would in future allow a little bit more time to be able to do that properly, which we found very useful because we are able to understand the process down to a very deep level. So again, without that deep level of understanding, it's very difficult to know where our waste in terms of losses were. And funnily enough, some of the biggest losses were actually hiding in plain sight. So in these cases, just metering may not have given us any benefit because the losses were already built into the process. So going back to first principles was absolutely the right thing to do. Where did we end up? We identified and designed process changes that would deliver about 37% reduction in the energy use of the two sites. And that was considered justifiable. So we could have done a lot more, but the cost balance would have been a bit more challenging. Some anticipated technology solutions like MVR and heat pump, which we are huge fans of, really didn't work out when we started to look at the heat and mass balance from the fundamentals point of view. However, opportunities did present themselves as well as we went through this process. We also realized OEMs don't often always have the solutions, and that's something I'll come to in a further slide in terms of measuring steam wastage. Investigating alternate manufacturing methods is something that was a big learning for us. So being in the food industry, a standard approach was always hygienic stainless steel, and all of those things that I think a lot of FMCG companies would be used to. What we've come to realize is, after trying several times to make that more cost effective, that we really need to be talking to a completely different group of trades and suppliers, and really looking to have as less of it as hygienically as possible. So using commercially available technology that's not exactly for its original intent, using it innovatively and revising. We revised down the scope of a couple of projects about 3 times to be able to get it to that sweet spot of being justifiable. So thinking big did cost us time and effort, and we had to redo the exercise a few times to get it down to the right size solution. But that's learning that happily share with everyone in terms of we did ask in the heat conference some of the experience from our New Zealand colleagues who are a little bit ahead of us, and it was surprisingly very similar. You touch hygienic installations and it becomes ridiculously expensive. The trick is to see how much we can do without being hygienic. So I'll step through a bit more that might explain that. So what were the general learnings for us? I did mention before that detailed process knowledge, heat and mass balance data should guide our solutions, but we tended to start with a few grand ideas of what we thought would have worked from energy audits. So one of the key learnings is energy audits don't give you the full picture. They are a top-down audit, whereas what we've done is a bottom-up, and we've been finding gaps that you'd expect to find from the 2 approaches. So vapor recovery and mechanical recompression is something we considered would have been a good idea for our dog roll cooking process, where there's actually steam that is drawn back off the process, or vapor that's being drawn off the process. So that seemed like a good idea at this time. But then as we worked through it, we found that the MVR technology was only really effective larger than 5 tons an hour of vapor recovery, which sort of precludes a lot of these processes at the moment. Hopefully, processes will get developed as we go along. Reciprocating compression solutions would be able to be applied for a smaller outcome, but one of the constraints there is they do require a positive pressure, and in these applications with vacuum, that really didn't apply. HB also had a similar experience with UHT milk sterilization, where it's a very similar process again, where direct injection of steam and recovery of vapor. The MVR technology was way too large, or the current state of the art is way too large for those applications. But watch the space in the future. Energy audits overestimate waste heat available. So I think that's something that we've come to realize over this exercise is when you try and extrapolate from doing audits based on asset sizes, it's not often reflective of a bottom-up calculation. The equipment doesn't always operate at maximum capacity. For example, a refrigeration plant usually rejects about 25 degrees, not 35 as design would call it. Looking at each process from first principles gave us the ability to identify a lot of opportunities that the top-down approach had missed. So whilst we found opportunities that didn't stack up, we also found new ones in that process. Installing metering, connecting and calibrating them as part of the study. Ideally, you'd want them done beforehand because it does take time for all of that to be installed and validated to then feed back into the study. So that's something to keep in mind. Often we do it as one project.
Raj, just a heads up that we'll try and keep to maybe 3 more minutes.
Okay. So a couple of the key projects, I won't go through a lot of the technical detail. More than happy for the pack to go out and happy to take questions from people even after the session. But one project that was quite a large saving was retort cooking, where cans or pouches or trays of pet food were sterilized in a retort process. Currently, all of that energy essentially is being rejected to the environment through a cooling tower, and that's about 900 gigajoules a week, or 58,000 gigajoules a year. So we've looked at a thermal storage system with 3 different temperatures and looking at storing that heat from subsequent cycles, boosting it, and reusing it in the process. So in that process, we will be able to achieve about a 40% reduction in the energy usage, but the infrastructure required to store that amount of heat in a 200 kiloliter tanks of hot water in the country would be quite easy to do. In the city, it does get quite a lot more difficult, and the distance and proximity does add a significant amount of cost to the capital. Something we did that was very useful was to do modeling of how all of these systems perform. So we used a 5-minute interval with 30-second calculations and produced a model of how these systems would operate based on existing representative production data. So that was very useful. But the big learning here is, Excel isn't the best tool for a lot of these, even though it does work and did work well with our ground up design. It isn't the best tool for the job. Great main learnings is we considered heat pumps to be a good idea at the start of the project, and we are huge fans of it. But essentially, what we found was with the TES design and optimizing the flows in the TES design, the amount of heat demand was fully being met by the TES. So there was really no need for a further heat source to be introduced. In this case, simple process engineering beats advanced technology. Not always, but in this case, that was the case. The second process that we really looked at is continuous tunnel cookers for meat products. Again, a lot of steam in this process. The key thing here being steam is lighter than air, and it's usually, if there's visible steam in the room, that is wasted steam, but this is one of the areas where losses were hiding in plain sight. But we did have a significant challenge in measuring how much steam in air was being used inside these tunnels. And OEMs really didn't have any measuring devices. There's a lot of set and forget sort of control systems. We looked at smoke detector technology that could be adapted, but it's a long way off. So it was a bit of a technical challenge to overcome here, which we did come up with an innovative solution to overcome, which is to condense the excess steam and use that as essentially a measure of how much excess steam, and using a control process then to maintain no more than a 10% excess, which would just make sure that air doesn't get into the tunnels. So this is something that would love for, if there's other people with similar experiences, would love to cross-fertilize and look at how that would work. It's a challenge that we believe we've overcome, but we'd love to talk to other people.
Fantastic. Thank you so much, Raj. I might pause there so we make sure that we give enough attention to our last case study. And Fabiana, you've got some time to go over so you can get your full slot. So at this point, we are going to hear from Fabiana, who helped support the feasibility study into the resource recovery facility in the red meat sector, which is for Bindaree Food Group. And this project received a $150,000 RENA grant, which supported a $310,000 study. So I'll hand over to you.
Thank you. Thank you, and good afternoon, everybody. So I'm here today to share with you a bit of a summary of the work we have been doing with the red meat processing sector. It's a little bit different from the conventional cover aerator lagoon approach for biogas, so it's a little bit innovative. There is no one else in Australia doing something similar. So I'm going to go through a little bit fast because there is a lot of detail here. So this is aligned together with a larger driver, right, from Australia and ARENA and AMPC and the processing plants to be able to reduce carbon emissions ultimately, but still meet their compliance, right? So the project drivers for ARENA, of course, is to support the transition to net zero and improve the supply of renewable energy. For AMPC, they want to have they have targets for the 30% of the red meat processing industry to be in renewable industry. They want to have 5 piloted initiatives implemented in the next few years and driving circular economy and everything. So, but for the processor itself, which we don't call abattoir anymore, so it's a red meat processing facility, the drivers are to generate additional income through the recovery of resources that are going to waste, establish a reputation as a leader in sustainable practices in the sector, boost energy independence as well. And well, we have also the reliability of cost efficiency by producing self-supply food-grade CO2, and of course ensure their environmental compliance. So the concept for the bioresource recovery has been developed in the last 6 years in partnership with the MPC, and we are studying that in several parallel projects. So this is not the only project we are doing. So there are many streams. So it includes separating the wastewater treatment, where we really focus on very strong pre-treatment steps to recover water for process and recycling options and irrigation. The high energy contents like the sludges, the fats and oils, and plus the solid waste that comes from the processing plant, like the pouch, the gut contents, the unedible offals, all these things that were going either to landfill or to composting. Now we are using a CSTR kind of anaerobic reactor instead of a pond. So there is no cover-related lagoons in this concept. We just use the high energy materials to produce biogas. So from that biogas, we can produce electricity and heat, of course, using a CHP engine, and also a byproduct called food-grade CO2, which is in very high value in the market at the moment. From the digestate, we also figure out that if we further process it into a biofertilizer, you can also generate income from there. So with this concept where we integrate the wastewater management, the solid waste management, and trying to maximize the resource recovery, we found out that they can also benefit financially by implementing this concept. So yeah, the water recovery plant, it's we are using a pre-treatment using an organic coagulant that doesn't have metals, so it's very easy to send it to the biodigester. We are using a conventional three-stage biological nutrient removal. So we partially remove phosphorus, and then we also do COD, BOD, and nitrogen. We are prioritizing ceramic membranes for the tertiary treatment because of the longer durability and lower energy footprint as well. And in the end, we end up with a Class A water production. So this is a critical part of the process, even though this project is not about wastewater, but recovering the maximum of the high energy content in the pre-treatment plant and pure water. The biogas plant and the bio-CO2 plant, they are really inspired on what's happening in Europe. And here I have a photo of a recent trip I had on behalf of AMPC to visit facilities that are similar to that in Germany. So they combine the biogas production using the waste from red meat processing, from dairy, and from agricultural waste, like the stubs from the crops. But they also have a solar farm attached to it, which is super interesting because they use the biogas as their battery instead of having a battery in the plant. So it is quite interesting to think of this concept, but well, let's focus back here. So in the biogas plant, we have the pre-treatment from liquid and solid streams. We have a bit of conditioning and pasteurizing to produce a safe product. We are using the Victorian guidelines for the safe digestate production. So we are ahead of the game already in New South Wales when this comes there. And the anaerobic reactors, they are highly engineered with mixers, with temperature control, the best of the breed, right? So we maximize the recovery of energy. And when you compare this type of reactors, you both increase the amount of biogas you can produce, but also the concentration of methane you can achieve into the biogas. So it gets super efficient. It's really interesting. And recovering CO2 by amine process in the end, and the post-processing for the digestate, of course, right? So what we have tried in this project, we had a series of different substrates. It doesn't look very appealing. It's close to lunchtime here in WA. It's a mix of the contra shear rendering material, the red trichanter to tallow, the manure, various solid byproducts, screen wastewater, the pouch and crop stubbles that they have on site, and the DAF sludge, right? So we mix all of this. The composition is about most of it is the DAF sludge, but there is a good variation and combination. This is good because in this way we are managing several waste streams that were going before to disposal facilities. So you are both generating renewable energy, but you're also preventing these things to generate methane in nature. So from that, you can produce around 8 million nano cubic meters of methane per year, the biogas per year, containing around 182,000 gigajoules per year of energy, which is around 2.3 megawatt hour in electricity in a CHP engine, and 2.4 megawatt hour thermal in terms of energy. And that is almost all the energy that the facility needs to operate. So if we can optimize a little bit more the co-digestion with more substrates, we might get into a fully renewable red meat processor in New South Wales. For the bio-CO2, it was not really inside this scope of this work, but it was very interesting because the fact we can recover the dry ice that is used for transporting the meat made the project super viable. The return on investment related to the recovery of CO2 is incredible. So we decided to keep it in the presentation here because that can add value for the wider audience. And the biofertilizer production as well, we realized we can produce around 5,500 tons a year, and we had a recent market assessment where we can get up to $4,000 per ton in retail for this kind of product, which is super interesting. So we did an economic assessment of this all this concept because, in our opinion, it doesn't matter if it's super nice technically. It doesn't stack financially. It's not going to happen, right? So we developed 7 different scenarios in different ways of combining the different parts of the project and also in the sequences on how we implement it. If we implement the full scale straight away, which scenario 1, or if we stage in 2 stages, which scenario 3, to accompany the industry growth, right? So I'm going to present just the best results here in this slide. So if we implement everything in one stage, you have to have an investment of about $60 million. In 2 stages, a little bit higher because you have all the mobilization costs that you have to do twice, right? Project management, site mobilization, and all these things. So there is a slight difference between one and the other. And the resources that you can recover from that are quantified here. And this is in current prices, and we didn't do a projection on what is going to happen in the future, but that can be more optimistic, I think. So from recycled water, you can have a revenue of around $40,000 per year. And that is considering that they can only recycle about 15% of the treated water. Everything else is going to be used for irrigation. And then the return on investment from energy is around $1.2 million a year for thermal and 1.2 for electricity. For the recovered CO2, that starts getting interesting. It's almost $3 million, more than $3 million per year. You can recover from producing your own CO2, and then you also have reliability on supply. You don't have issues when the market is fluctuating. From the biofertilizer, we did this assessment is a lower price, so it's around $1.7 million a year. But we have now a different number based on a market research that could go up to like $18 million a year revenue from biofertilizer. And then I also have savings in disposals of around $25 million a year, plus carbon credits that you can obtain from replacing the fossil fuel energy with renewable. So in terms of CapEx and OpEx and return on investment, the scenario 1, meaning implementing the entire system at once, is the most attractive financially. You have a very high return on investment. The payback time is a bit long. It's about 7 years. And that's because you have the initial implementation of the project where you don't have any revenue until you have startup. So there is a long time, like almost 2 years that you are investing CapEx and then you get operational. Scenario 3 here you can see is if you only do what you need to do for complying with environmental regulations. So it's not attractive from the financial point of view. And the scenario 6 is implementing in 2 stages, which is accompanying the growth of the industry. So there are differences. So scenario 1 would be the most attractive with a very good return on investment in total, a net present value of $222 million. That means invest $60 million now and you return over the life of the project $220 million. Which is quite attractive considering that until now, waste management and all these things, they are all only a liability normally. And here in the integrated approach, we can make it another source of revenue for the industry. So here is just a summary on what we can achieve in terms of recovering resources. So we can recover water, we can recover biogas, electricity, CO2, and biofertilizer in different forms. And here, what we thought of doing is, okay, Bindaree Food Group is one of the 10 biggest red meat processing plants in Australia. So what happens if we do it for smaller producers? So how can you adopt that in a different scale of production, right? So the scenario we model is around the larger ones here, close to 100,000 tons of processing per year. So what happens if you go down, like a medium-sized food processor, for example, around 40,000 tons of hot standard carcass weight? You still have a good return on investment. It's a little bit longer. You get closer to 10 years, but you still can have a positive cash flow, a positive return in the end, even though it's a longer payback time. So it is applicable. This concept is applicable, I think, for medium to larger size facilities, which is the majority of the production in Australia in terms of tons of carcass weight. In terms of the income distribution per stream, you can see here that basically half of it in this scenario is due to the recovery of bio CO2. So that's very critical that when we assess an opportunity like that, we need to understand if there is a market or not for the bio CO2 because the feasibility can change. Another good part is from biofertilizer, from the energy, and from the carbon credits and the recycled water and savings from disposal. So it is a combination of factors that make this project feasible. If we only look at energy, it's not. If we only look at the CO2, it's not. But when we put all together in a matrix, that becomes very attractive. Next one. Next slide. I didn't see the next slide there.
I think we can see turning risks into opportunities in the red meat sector.
Okay, sorry, but it didn't flick in my here. So I just want to close up with a message here that there is still some people that are a little bit afraid into jumping into doing very different things, right? It is a bit nerve-wracking because the numbers are very high, the capex is high, there is a lot of investment and risk to be taken. But I think we are in a way that we need to do the jump and then do what we can to surround ourselves with experienced people to walk us along the journey. And that's the final message here for me. Thank you.
Thank you so much. Super informative. So we've got a bit of time for questions now, and I encourage you to ask anything specific in the Q&A chat. If we don't get to it in this time, we'll do our best to make sure that it's answered. And perhaps just to seed those questions, I had a question that I wanted to ask. Raj, you mentioned that data modeling as a service could be a potential kind of gap in the market in this space. Just be interested to get your thoughts and potentially the other speakers' thoughts from your experience on what that looks like or could look like.
Yeah, from my point of view, as a medium sort of size engineering company, it's quite difficult to invest in that capability yourself. So having an energy network that has that capability, rather than having to do it commercially, through a university or something like that, would be really handy. Where you could actually build that and at a reasonable cost, and not have to have a huge amount of funding to be able to do it.
Yeah, Tanya and Raj, we see this being done by different universities, ISF, and I know people. There's some good engineers working for the likes of Flow Power, good at crunching these sorts of numbers, but I haven't seen any easily available product there. Is it we're talking just a Python type programmer here, Raj, or where how far does it need to be?
It's just take that and not relying on a lot of manual calculations to just be able to automate that, so you can do multiple scenarios really quickly and optimize the model rather than do it by trial and error.
Happy to get some more info off you, Raj, because we know the people that do these sort of models through the uni and like the idea of preparing them for more open use. So
yeah,
if I can
that'd be nice.
If I can just tip in here, what we are using here very successfully is Power BI. It's a really good tool to manage large data in a very friendly interface to users. So yeah, maybe have a look at that too.
No, thanks for that build. That's useful.
That's helpful. And maybe on a similar topic, it would also just be good to get the panel's perspectives on how much time you need to give to that initial mass and energy balance to actually getting the right data points to start the work in a informed manner, and any learnings that you'd share to the audience. Maybe Megan, do you want to kick off?
Sorry. Huon, you might want to.
Yeah, happy to. So it obviously depends on complexity of plant. The more complicated or involved the plant, the more time that will take. It also, I think, reflecting what Raj has said, if it depends on the level of detail you need to achieve in terms of how much confidence you need in that measurement outcome. Taking a modelling approach is usually what we do at the beginning because the measurement doesn't exist. What we were able to do as part of the project with G&K O'Connor is go and complete those measurements, but that took a year. So getting a metering system specified, purchased, installed and functional took a very long time, and a plant that in some cases didn't have a PLC when we walked into an area of plant. So there was nothing there. So that's a long process. And has it produced a more reliable and trustworthy outcome? Certainly. I don't think it's the first step. We first completed an energy audit, which used a modelling approach, such as Raj has suggested, and that can be done in 1 to 2 months.
Yeah, we regularly see that the metering is not in place to do that a decent energy and mass balance. And we're really pleased when we see like the likes of New South Wales government saying that they're going to support this, and they support either with management metering plans and then implementation backup as well, because so often there's either insufficient steam or temperature meters, or even a very simple plant, very simply having a pulse meter on the gas totalizer out the gas meter out the front. That's missing. So just that quarterly or monthly gas bill is not going to cut it at all.
It's as I said, it's down to the complexity of the process, but the unintended benefit we saw was that if you were measuring a process, assuming that the process was already optimized, which in a lot of people's minds it was, then we would have missed that opportunity of the saving, because it was seen as part of the standard process as opposed to looking under the bonnet there.
Mm-hmm. And what we do see, though, if you don't have that metering and you don't go to that trouble, then you're down for the very much doomed like-for-like approach. As soon as you're looking to replace that 6 megawatt boiler with a 6 megawatt MBR heat pump electrode boiler, doomed. Your project will very unlikely to stack up. And so if you don't have that metering in place, and that $100,000 of metering easily pays for itself, saving you millions of dollars in that in the technology investment.
The other thing we found, of course, is that doing it that way, whilst it seems like with putting a lot of effort in, it's a lot cheaper than going for the substitution, as you said, going for a full MVR or going for a electrode boiler for the full size. So payback is one of those things that I find quite challenging to address, given still the mindset is very much that of a 3-year payback sort of thing. So getting everyone to see that energy efficiency, whilst the payback may not always meet the 3-year threshold, is a downside cheaper than going for full decarbonisation another way. So it's always the first step, but it's not something that I found an easy message to get across to everybody.
Got it. That makes sense. In just the last 2-3 minutes, I would just like to have a small plug. If we can go to the QR code for the survey, if you can take, I think it'll take you 30 seconds to fill out a brief survey. The carrot here is that this doesn't just ask you if this event was useful, although that is useful to us. It also asks for what area of the industrial landscape you play in, and if you have any appetite to progress a concept with ARENA for funding. So if you can add that in, add your details, we can queue up the right conversation to see if there's any opportunity to support you in this process to progressing the right opportunities and solutions in industrial decarbonisation. So I'd encourage everyone, whether you click the link, which will pop in the chat, or whether you scan the QR code, that will be most valuable for us and also help inform the type of events and information that we can progress with going forward. So I'd also just like to thank you so much to Jared and then to each of our speakers. I think really valuable to see the type of information out there, and then also what it looks like when you start doing this in practice and the hurdles that you might encounter. So if you have any specific questions or if there's more information that we can provide, we'll share the content and the associated pages publicly on ARENA's website. So if you fill in the survey, you'll also be able to get that material and a snapshot of the information that was shared and the key learnings that came from it. I think that is about it from us. So once again, just like to thank everyone for their time and for joining. Hope it was useful. Very practically, if you do want to reach out to ARENA, feel free to send an email to industrialtransformation@arena.gov.au. It's myself, some of my colleagues on the other side of that email, so we'll be able to guide you and answer any questions that you have. I'd also really encourage you to just have a look at the ARENA Industrial website. It's got guidance, FAQs, program guidelines, so a whole wealth of information there that will give you a better idea of what we look for, how we consider merit, and then how you actually work through the ARENA process. Thank you so much all. We'll call it a day.
Thank you.
Thank you.
Thanks. Thank you.
Thank you.
Is there spec, by the way?